wanted to apologize for not being able to be to class today. Just had some chaos at the house and I need to attend to it, but it's okay. I will make it up on Wednesday. I will do lots of drawings for you guys, but the show must go on. And we are going to continue our conversation on these autonomic nervous system drugs. And now we're going to kind of move into how drugs can impact neurotransmitters. So we spent a lot of time in class kind of drawing these different types of receptors, really focused on ionic and nicotinic and adrenergic and G-coupled protein receptors, and we kind of drew a lot of pictures talking about all of that. So now we're going to see where these sites are for drug action along those pathways, specifically in neurotransmitters and somatic signaling as well as autonomic nervous signaling. Not going to talk too much about what goes on in the brain. That's a little very complex and it's kind of beyond the scope of this class, but we're going to kind of clarify a few more of these concepts. So let's move on. So what we're going to talk about now are how drugs impact neurotransmitters, and they will impact several parts of the neurotransmitters. So we're going to talk about how drugs can either stimulate or inhibit certain enzymes within a pathway. They can impact the storage of certain neurotransmitters within their vesicles. They can assist in accelerating or decelerating precursors that make neurotransmitters or make other types of chemicals that are going to bind to a neuron to have some sort of a physiological process action. We'll talk about how certain drugs can impact the release of neurotransmitters or impact reuptake and basically inhibit the reuptake of certain drugs, which will turn off signaling. So these are the things that we're going to focus on primarily today, and we're not going to go into anything very specifically. Rather, I'm just going to say that there are drugs that will be agonists or antagonists for these particular stages of neurons, either communicating with other neurons, communicating with other organs, or communicating with skeletal muscle. So this is kind of what we're going to talk about in the first portion, and let's move on. So there are many medications out there that will basically stimulate or inhibit enzymes. And if you can see here, you have this picture. I kind of drew this picture for you in class on the chalkboard, or the whiteboard, I should say. We have this choline acetyltransferase. And what does this enzyme do? Well, this enzyme helps take choline and take acetyl-CoA that we get from the mitochondria, right here, acetyl-CoA, and it helps combine those two to make acetylcholine. So one of the enzymes that can be inhibited in this process would be this choline acetyltransferase, right? And what does that mean? Well, that means that we would have less acetylcholine being put into these vesicles, right? So we can inhibit this enzyme here. I mentioned in class that we can also inhibit this enzyme, which is acetylcholine transferase, right? I'm sorry, esterase, not transferase. And this enzyme can also be inhibited, which means that we would slow down the separation of acetyl and choline again, because this enzyme right here, this separates the acetate and the choline, and it basically makes that neurotransmitter inactive. So if we wanted to keep this neurotransmitter kind of in this gap a little longer so that we can stimulate some of these receptors for a longer period of time, well, we could irreversibly inhibit this enzyme, right? So one of the first targets we could talk about, and you might read it in your papers as you're preparing for your presentations, is we can target these enzymes. And again, we don't want to turn them off permanently. We would want to slow them down for a time or accelerate them, increase them for a little bit of time, and then go back to the normal physiology. So these would be reversible medications that could temporarily alter the course of this enzyme and temporarily alter the course of this enzyme. And again, we have these antagonists and we have these agonists that will increase or slow down the action of these enzymes. So that would be one of the first drugs that we can use to target enzymes, and we can stimulate or inhibit. So next one would be precursor availability. So let's look at that one. So if we look at this cell here, we have an enzyme here that is basically taking a substrate and it's making a new product. And in this one, we're talking about dopamine. So we're talking about the synthesis of dopamine. Well, when we're talking about ADHD and we're talking about ADD and we're talking about mental conditions where we don't have normal physiology, well, one of the running theories is that we have a decrease in the synthesis of dopamine, right? So how can we increase, sorry about that. Let me go back. How can we increase, I'm going to just get my pencil out here, the production of dopamine? Well, we have to look at the precursor of what makes dopamine. So we can take certain drugs, like this drug here. We'll just say this is drug Z, right? And drug Z will increase the precursors to dopamine, and as a result, we will get more dopamine. And hopefully that could regulate some of the behavior that people who have low levels of dopamine might exhibit, right? So this would be a stimulator or stimulating the synthesis of a particular molecule, right? So we can kind of give the cell a little bit of help in the synthesis of certain molecules with these medications, right? So we talked about stimulating or inhibiting certain enzymes within neuron-to-neuron communication. We talked about precursor availability, and I'm going to show you one more thing on the precursor availability, but also we're going to talk a little bit about reuptake inhibition as well. So let's take a look at that, and let's look at a very common prescription for individuals that have ADHD or ADHD or other types of neurological disorders. So if we look at the slide here, we can see a presynaptic terminal and a postsynaptic terminal, and we can see that these vesicles are filled with dopamine, right? And we know that Adderall is a precursor accelerator. So Adderall, which is a very typical drug that is given for people with attention deficit disorders, is going to accelerate and assist with dopamine production, right? Which means that these vesicles are going to be filled with dopamine, right? So when we have the secretion of dopamine, one of the first things that shuts off dopamine is an excess amount of it here in the synaptic gap between the pre and the post neurons. So one of the other medications that is used to help dopamine basically increase its message is something called Ritalin, right? And what is Ritalin? Well, Ritalin is a reuptake inhibitor. So if we look at this neuron here, we look at pre and post, we can see that dopamine is being secreted across this cleft here to the postsynaptic terminal. And what Ritalin is going to do is this is going to block the reuptake receptors. So this Ritalin goes in here and it blocks the reuptake of dopamine, which means we've increased the amount of dopamine with Adderall, and we're blocking the reuptake receptor here, which is going to let that dopamine secrete more and stay more active in between these two neurons, right? So this would be an example of a precursor that's going to increase dopamine production, and also a reuptake inhibitor, where normally dopamine would be retaken up into the neuron after it has fired, and this is a feedback mechanism which would turn off the secretion of more dopamine. So by blocking that and increasing that, we get more of the dopamine binding to the dopamine receptor, and that message gets to continue on. So another sort of target for medication is storage. So you can see here that we can increase the storage of certain vesicles in the neuron. We can increase the storage of neurotransmitters in there. So you can see here we have a lot of vesicles that are kind of populated within this neuron here. And well, how do we do that? Well, certain drugs can increase but also decrease the amount of neurotransmitters or any sort of chemical that is used to be secreted from one neuron to another. We can impact how much of that is put into storage. And we also might have some drugs that will disrupt that vesicle storage, which will therefore disrupt vesicle transport, or we could do things that will basically increase it. So that would be another type of target. And there's a drug here called Reserpin, which is used for high blood pressure medication, but used for other sorts of disorders as well. And this medication, if you look over here, here it is, Reserpin. Here's the drug. And that drug is going to bind to the vesicle. So you see the vesicle here. And you can see that the Reserpin is kind of bound to the vesicle here. Well, what this particular drug does is this is going to be an antagonist. This is going to slow down how much norepinephrine can be put inside of a neuron's vesicle. And it's also going to slow down how much of that norepinephrine can be secreted. So this is going to stop hyperactivity of norepinephrine being secreted and hyperactivity of norepinephrine being stored in these vesicles. So this would be slowing down the nervous system, right? And this medication is something that would particularly bind to the vesicle and slow down how much, and you can see here we got some dopamine coming in, right? And we have norepinephrine, and this is going to slow down how much dopamine can get into the vesicle and how much norepinephrine can get into the vesicle, and therefore just kind of slowing down the entire process of secretion of these messengers. So let's move on to the next one. There's also medications that can impact the release of vesicles, right? So we're kind of looking at a whole bunch of different things here. And if I go back to this one here, this particular slide, we can target the enzymes that either help make a neurotransmitter, or we can target an enzyme that can help decrease the activation of a neurotransmitter, right? So we can kind of shut this off and shut this off. We can impact the storage of certain things within a vesicle, right? We can have certain drugs bind to the vesicle. We can accelerate the precursor, right? So we can, if we wanted to increase the acetylcholine and we wanted to kind of help make more of it or make less of it, right? We can kind of impact that there, which is essentially what this would be doing. We can slow down or accelerate the release of these neurotransmitters. And we could also block these receptors down here that are receiving this, or we can help them and increase their signal, right? So everything in here is targetable, right? The chemical, the enzymes, the vesicles, the secretion of the vesicles. We can stop the enzymes that want to break these chemicals down, and we can stop the receptors that want to receive those chemicals. We could also accelerate these things, right? So the reason I keep showing you these pictures is because everything in here is targetable. Everything can be manipulated with these neurotransmitter drugs or these autonomic nervous system medications. So let's go back to how we can impact the release of certain drugs or of certain messengers, chemical messengers. So we know that when a neuron fires, we have an action potential that kind of comes down the neuron, right? The presynaptic neuron. This would be post, but if you look here, this is a cardiac myocyte. So this is the sympathetic nervous system communicating with a muscle cell in the heart. Well, one of the things that has to happen before this vesicle can release its payload is we have to have this action potential depolarize the calcium channel. And when we depolarize the calcium channel, calcium will rush in. And then when calcium rushes in, these vesicles will move to the membrane and release their payload. Well, we can also influence the release of these vesicles by influencing the calcium ion channel. So we can deliver certain drugs that will either accelerate it, so we can get more vesicle release and more neurotransmitters communicating with the heart cell, or we can also inhibit it, right? We can slow it down. If we have someone that has hyperactivity of the heart, well, maybe one of the things we do is we deliver this calcium ion channel, and this will impact the release of acetylcholine, which will then impact how much of it binds to its receptor, and ultimately this will slow down contraction of the heart. So even the ion receptors, the ion channels are targetable, and this is one of the things they do with people with high blood pressure or hypertension, right? So this particular channel is going to directly impact exocytosis of this neurotransmitter, right? And what else could they do? Well, they could also give a drug that is a precursor inhibitor that will reduce the amount of acetylcholine that is created in this neuron, and use that in tandem with this to slow down the production and the release of acetylcholine to the cardiomyocyte, right? So now you guys are getting a little bit of hopefully you're getting a better understanding of how these things can all work in tandem, but we really can't understand it unless we understand the anatomy of an action potential in the neuron, and we understand how that message is received with these receptors, and that message is delivered downstream of whatever organ or cell that we're talking about. So I will move on to the next one now. And if you can look at this screen, obviously this is incredibly complex, but this one here is looking at those G-coupled protein receptors, which we're going to talk about a little more in depth today. Those are also called muscarinic receptors. And we can see that a G-coupled protein receptor here and here, we can see the G protein here, right? We can see the G protein here. We talked about in class how when this is activated by acetylcholine, well, this G-coupled protein receptor is going to become active. It's going to release its properties. The G protein, right, the gamma protein is going to interact with adenylate cyclase, and then this is going to create cyclic AMP, right? So you can see right here. Well, cyclic AMP is targetable. If we have a downstream signal that is dependent on cyclic AMP and that amplification is too much, well, we can turn that down by targeting it with medication, right? Certain types of drugs will target that. And we can turn it up or we can turn it down. The same is true for diacylglycerol, which is also another target that receives a message from adenylate cyclase. We can target that, DAG, which is big in diabetes. That's one of the things they turn down in diabetes. So they'll deliver a drug that will kind of reduce the activation of that, right? And then we can also have IP3, which is right here. And IP3 is another targetable protein that we can kind of turn up and turn down. And keep in mind, IP3, DAG, and cyclic AMP, they're all activated by these G-coupled protein receptors. So the reason I want to show you this is maybe while you're reading your papers, getting ready for your first presentation, they'll be mentioning these targets and what they do. And just keep in mind that we have certain medications that can activate them or deactivate them or slow them down, or we can irreversibly bind to them and turn them off for a little bit. And then that medication will leave and they'll turn back on. Okay, so now we're going to repeat a little bit of information that we talked about in my office on Wednesday, and we're going to talk specifically about cholinergic pharmacology. And this is really highlighted quite a bit in Chapter 3 in your textbook. So we kind of already identified this, and I drew you what these were, but now let's get into a little more detail so you understand it a bit better with what you might be reading in your papers for your presentation. So This pharmacology is referring to drugs that are impacted by acetylcholine, essentially. We have two types of cholinergic receptors, and one is the nicotinic, which we've talked about. We know that that's on skeletal muscle. And the other one is muscarinic, right? So you can see here that we have a muscarinic and then we have a nicotinic, right? And both of them share the same ligand, which is acetylcholine, and they have different signaling properties. So muscarinic is a G-coupled protein receptor. If we count, we can see those 7 transmembrane portions of that protein. We know that it's going to activate the G protein, and the G protein is going to activate cyclic AMP. In this particular case, you can see here that cyclic AMP activation has been shut down. So we know that this would be a muscarinic antagonist, where it's turning down the property of this receptor. And then you see the nicotinic receptor over here. Acetylcholine can bind to it, but this one is more ionic based. So we know that ions are going to pass through, particularly sodium, and it's going to increase the polarity or the charge inside of the cell, and we're going to have an action potential, right? So those are the two major types, but within the muscarinic and the nicotinic, there are several subtypes, and you're probably going to run across a lot of those in your papers. So let's talk about the difference between those. We know that they belong to the same family, and you've seen this before. I'm just showing it to you again because as we get further into these slides, you understand things a little better. The nicotinic receptors, those are in skeletal muscles, right? So if we look here, that's somatic, and we know that there's acetylcholine, and it will bind to a nicotinic receptor on skeletal muscle. And we know then we'll have depolarization of the sarcolemma, and we will have voltage-gated ion channels open up. And once they open up, we'll have sodium rush in, and the sodium and the potassium will rush out. That will go down to the transtubules, and then we will get calcium released from the sarcoplasmic reticulum, and then we have contraction, right? So you guys are very aware of that. So the nicotinic receptors are also within the sympathetic and the parasympathetic. So if we look here, sympathetic and parasympathetic, here's the acetylcholine, and we can see that both of those share nicotinic receptors. They are also a part of the autonomic ganglia, and what that means is we have here the pre and the post, right? We've talked about that. So here's the postganglionic neurons, here's the pre, and here's the post. Well, nicotinic receptors play a major role in relaying. So this would be the central nervous system up here, right? Central nervous system. We will have a signal come from the central nervous system to the peripheral. That signal will come down here. We will have this chemical messenger released. It'll bind to the nicotinic receptor. That will result in sodium rushing into the cell, and that happens in both the sympathetic and parasympathetic, and that's what that means by the autonomic ganglia. Okay, we see nicotinic receptors also in the central nervous system, and these are ion-based. Generally, sodium, potassium, calcium, those types of things, okay? Now, when we move into the G-coupled protein receptors or the muscarinic receptors, which are also let me go back just to kind of show you. These are also cholinergic receptors, right? So there's lots of words here, right? So when we see these receptors, these are primarily found in the parasympathetic nervous system. So if we look over here, here's parasympathetic. Okay, so here we see nicotinic, but down here we see muscarinic, right? So the parasympathetic nervous system is occupied with a lot of those G-coupled protein receptors. But if we look at the sympathetic, we have the adrenergic receptor, which we've talked about already as well, right? But that is not a cholinergic receptor. That is responding to norepinephrine, right? So the sympathetic nervous system, it will use acetylcholine for the pre to post ganglionic signaling, but then once the sympathetic nervous system gets to an organ or a tissue, then it uses norepinephrine. So those are some of the differences. And the G-coupled protein receptor is in the brain, the gut, and the glands. They're all over the body. Lots of them in here, lots of them in here, helps with digestion. Lots of them in here, like glands with your salivary glands when you use to salivate. So just different locations, and they both belong to the same family. They have a slightly different structure, and they also have different signaling, but the common thread is this acetylcholine. Okay, so when we are talking about these types of drugs, here's that thing that we were talking about again, right? That same picture I showed you over and over and over again. These drugs block the action of acetylcholine, and they do so by binding to cholinergic receptors. Therefore, they inhibit the activation of certain things. So, for example, if we have the inhibition, if we have this nicotinic receptor on the muscle, and we have this muscarinic receptor on a different organ, the cholinergic drugs are going to interfere with acetylcholine, and they're going to interfere and bind to these receptors to stop their signaling, right? So that's where the action is going to be here and here. Well, they could probably also bind here and here, right? Because nicotinic belongs to the cholinergic receptor. So these are the points where we can have the inhibition of certain things. And in this picture here, we can see that these antagonists are used right here, right? So they are going to bind to the receptor, and they're going to compete with acetylcholine. So again, we saw that we can inhibit this, we can inhibit this, we can inhibit this, we can accelerate this or decelerate this. We can influence how this vesicle is stuffed. We could also inhibit the vesicle itself. We can inhibit or accelerate the presence of acetylcholine in the gap here because we can shut this off, or we can speed that up, right? So every part of this, like I said before, is targetable, and these cholinergic antagonists and accelerators, they're going to compete here on the actual receptor, okay? Okay, so I found this, and I thought this was a pretty interesting way to think about these receptors and this type of drug and cholinergic pharmacy. So we know that the receptors will the drug will either mimic the action and accelerate this, or it will block the action, right? So if we're talking about cholinergic agonists, right, and these things are going to accelerate the action, well, I want you to think of this sludge word, and I'll tell you exactly what that means in a moment and what it does. Now, if we want an antagonist, right, we want a cholinergic antagonist, well, that's going to shut off those receptors. And I want you to think of the word dry, so sludge and dry. And let's kind of look at this for a second here. So when we talk about these agonists, right, these things that are going to accelerate the parasympathetic nervous system, and it's going to accelerate it by increasing acetylcholine, right? That is going to do things like increase salivation. We'll have more tear formation. We could have more urination. We could have an increase in diarrhea. We could have GI distress, right? We could have vomiting. So what I'm trying to show you here is that acetylcholine is responsible for all of that, right? So if somebody is taking a medication that they want to kind of reduce the amount of vomiting they have, well, then they might take an antagonist to block this receptor to get that to slow down, right? So basically it's called sludge because when a person has an excess of acetylcholine, we have fluids kind of coming out from everywhere, and that's all here, right? So that's those. I'm just giving you an idea of what this thing does, this chemical can do in the body. And when I told you to think of dry, right? When I told you to think of dry, if we shut off this signaling, right? If we turn it off, well, then these things will dry up and we won't have it. So an agonist could increase all of these things and an antagonist could decrease all of these things. And that's how we hijack those receptors in the parasympathetic nervous system to turn these things on and off, or turn them up or turn them down. So if you look at these receptors here, this would be an antagonist. If we had an antagonist drug and it was binding to, what is this here? What kind of receptor is that? You see the G protein down there, right? If it was binding to a G protein, this would increase, right? Because it's an agonist. So we can have a drug bind to this receptor and increase that receptor's signaling. Now, if you look on this side here, this kind of shows you how this works. So this neuron, when the neuron can be, if we don't have enough acetylcholine in the neuron, well, then we can introduce the drug, and the drug can bind to the receptor to increase acetylcholine's signal, right? So that would mean that your natural acetylcholine and the drug, right, and in this picture it's called the cholinergic agonist drug, these things would work in tandem to increase the cellular response to acetylcholine. So in this case, we would have this CAD, and CAD can bind to this receptor. And I'm going on this side because the M1, M3, and M5 are different types of G-coupled protein receptors, and the M2 and the M4 is another kind of family of protein receptors. Here's what they do, right? So if we activate this one, we can increase adenylate cyclase, we can increase MAP kinase, we can increase calcium channels opening. So they do different things, and you'll probably be seeing that while you're reading your papers. But most importantly, just generically, is when we have an agonist working on a muscarinic receptor, it is going to work in tandem with what is being secreted to increase what happens in the cell. And again, that could be increase adenylate cyclase, which would increase cyclic AMP, right, that secondary messenger, which could increase how the cell responds to that secondary messenger. And again, the same is true for an anti-cholinergic receptor or an anticholinergic drug. So here's the anti-muscarinic drug. Again, that's the same thing as a G-coupled protein receptor, and you can see that the neuron is secreting acetylcholine, and we have the anti-muscarinic drug binding to those receptors and competing with acetylcholine binding to those receptors. So they're blocking that chemical signal. So that's what an antagonist would do, right? And if we were thinking about this sludge thing again, if we had the antagonist, these things would all slow down or dissipate or dry up. And if we had an agonist, these things would be increased, right? So there are times where we do want to increase, not purposely, but diarrhea. There's a lot of STI medications out there that when you take them by mouth, you will have, or you take them orally, you will have severe diarrhea, which means one of the agents in that medication is a cholinergic accelerator or an agonist, and that's one of the reasons you're having an increase in diarrhea. Like we talked about with the dry, right? We talked about these things here. If it's dry, well, if somebody is taking a inhibitor, or we're taking an antagonist, well, these individuals can't seem to pee, they can't spit, and they can't poo. So they get constipation, right? So that is how that could be one of the side effects of a certain type of drug.